Hello, this is StarTalk All-Stars Edition. I'm your all-star host this evening. Carolyn Porco is my name, and I'm a planetary scientist and the leader of the imaging science team on the Cassini mission, which is, as we speak, in orbit around Saturn. My co-host today is Chuck Nice. Thank you, Chuck, for being here.
Well, thank you. It's a pleasure to be here with you, Carolyn, definitely.
Well, I'm so glad to have you. Today, we're going to talk about some of the fascinating discoveries we've made on Enceladus with Cassini. And to help us out in this discussion, we have Chris McKay from the Ames Research Center in the Bay Area. He's astrobiologist extraordinaire. Chris spends his time scouring the deserts of Earth from Antarctica to Siberia, Namibia, Sahara, trying to understand those places on the Earth that might be like Mars in their environment and wondering how life can thrive there. He's been involved in conjuring what kind of human mission back to Mars might be like. This is a mission that would be piloted by humans. He's involved in that. And I've invited him here today because he is my cohort for the last 11 years in trying to get people to pay attention to what we have found with the Cassini mission on Enceladus, which is a small moon in the Saturn system, no bigger across than England, and why this small moon presents to us the most promising environment in the solar system to actually search for life or evidence of prebiotic chemistry. So welcome, Chris.
Thank you, Carolyn. It's a pleasure to be here talking with you.
Yes. So we've gathered your cosmic queries about Enceladus and astrobiology from various social media. That's right, Chuck. Haven't we done that?
That's exactly what we have done. And we have people from all over the internet who have submitted their questions via Facebook and Twitter and you name it, whether it's StarTalk.net. It doesn't make a difference. We take them. And they all want to know about Enceladus and more. You know, astrobiology and more. You know, people see your name and, you know, some people just want to know about Cassini and some people want to know about Saturn. And so I know that we're kind of focused on Enceladus, but, you know, when you say, when people who follow us, when we say Carolyn Porco, they immediately think Saturn because Neil calls you Madam Saturn.
I'm Madam Saturn. For the rest of my life, I'll be Madam Saturn. It's all right. It could be worse.
It could be a lot worse.
It could be worse.
So let's take our first, you know, we always like to have a Patreon. For those of you who are interested in supporting us on Patreon, by doing so, you get to do cool things like you get invited to parties that we might throw, or you can submit a question for our Cosmic Queries, and we will make sure that we read it because you gave us money.
That's the basic transaction in life.
Right? That's a basic life transaction. You gave us money, and now we're going to do something for you. So this is from Luna McIntyre, who says, do you think there are parallels that can be inferred by whatever is found with the Europa mission? Since the liquid oceans on both moons, I suppose both moons, she means Enceladus and Europa, seems to be due to tidal heating. So are there any, first of all, is that the case? I mean, are both moons, are there oceans created by tidal heating? And are there any parallels that we can draw or infer from the similarities between Europa and Enceladus?
There are a tremendous amount of parallels that we can draw. They are, in fact, both heated by this mechanism of tidal flexure, which is why they have oceans within them, and both of them have oceans. And I would say it goes the other way, that we have been nearly a dozen years now exploring up close and personal Enceladus with the Cassini mission, and with an amazing suite of 12 investigations on the orbiter that have been brought to bear over the course of those dozen years. And we know a tremendous amount about Enceladus, really far more knowledge about Enceladus at this point in time than we do about Europa. But I'll turn this over to Chris, because Chris also has a lot to say about this topic. So what do you have to say?
Well, imagine sometime in the future when we find life on Enceladus, we find life on Europa. Are they the same life? Do they represent a common origin? Or did life start independently on both of these water worlds? Or did life start on one and not the other? So I'm always focused on the biology questions, and a comparison between worlds is the most interesting possibility in terms of what kind of questions we can ask about biology and compare these two water worlds. And then, of course, we'd want to compare them to Earth as well.
Yeah. And let me just remind people that why we've gone so goo gaga over Enceladus, and
Yes.
that is because we found that it has 101 tall geysers that are erupting from its south polar terrain, which is an area, if you were to scale Enceladus up to the size of the Earth, it would be like the latitude of Tierra del Fuego and everything south.
Wow.
Or if you were biased towards the northern hemisphere, it would be like Edinburgh, Scotland, and everything north.
Wow.
So imagine having 101 enormous geysers erupting from the terrain that's that large. And once we found with Cassini these geysers, and we knew that the particles that we see in our images were accompanied by vapor.
Right.
And they formed this enormous plume that went ultimately tens of thousands of kilometers into orbit around Saturn. We took Cassini and we went barreling through it.
Right.
We went barreling through it time and time and time again. And we've been able to collect material and measure the contents of the vapor, measure the contents of the particles, measure the characteristics of the particles, how big they are, how their size is distributed above the surface. And all this information has finally told us where we are right now. We know we have a global ocean under about 35 kilometers worth of ice. It's salty. It's salty like the Earth's ocean is salty, and it has organic material. So it's got all the formal requirements of what in the NASA world, the NASA universe, we call a habitable zone. And that ocean is accessible now. All we have to do is fly through it again with the proper instruments.
Right.
Better than we have on Cassini, to measure it with a greater precision, and start asking really interesting astrobiological questions. Chris, what are some of the things we could do if we had a mission that went back to Enceladus with proper instrumentation? What kinds of questions do we really want to know?
Well, I think you said it well, Carolyn. We already know it's habitable. We already know it has organic material. We already know it has liquid water. We know that liquid water is habitable. So the follow-on questions really go right to the biology. Is it inhabited? Does it have life? And then the challenge is, how do we search for life? Well, we can search for life using molecules and tools that we develop for characterizing Earth life. But it'd be nice to also have a capability to detect life if it's not Earth life. So then the question becomes, how do we detect life that's similar to Earth, lives in water, made of carbon, but is not directly related to us, doesn't have our DNA? And I think the answer to that is to search for amino acids and search for their handedness and see if there is a enrichment of heavy, complex amino acids in the plume of Enceladus, and then to see if those amino acids all have the same handedness, which is a clear signature of biological selectivity.
When you, from an astrobiological standpoint, what would be more desirable? To analyze these components flying through these plumes, or capturing the water and bringing it back?
Good question. That's a very, very good question. There are people out there, groups of people, one group I know of that are looking at the possibility of a sample return. It's not a trivial thing to do because there's a lot of concern if you bring a sample back to Earth. You don't want to have an Andromeda strain scenario where you contaminate the Earth. So, that has to be done carefully. But
those Earthlings were really something special until they brought back that old Enceladus water.
Really, that was the beginning of the end. The instruments that we have on Earth are far more sophisticated than the ones that we could carry on a spacecraft. So, so Chris, in fact, has been a big proponent of a sample return mission.
But as Carolyn points out, one has to be extremely careful in bringing back a sample from an environment that we think could have life in it, and that environment is very similar to Earth's ocean. We've never done that before. We've brought back samples before, but we've never brought back a sample from a habitable environment. So this is a new challenge, and we have to proceed extremely carefully with it. So I think the next missions to Enceladus will not be sample return. They will investigate the plume in situ, following up on Cassini, but they will be designed to search for life, unlike Cassini. Cassini did a fabulous job. It was a wonderful, an unexpected find, and its ability to investigate it surprised all of us. And now we're back with a mission that's based on what we know and search for life in the plume. And then, meanwhile, think about how we bring a sample back safely, because ultimately we have to do that.
Yeah, can I just make a plug for Cassini? Because as Chris said, the instruments on Cassini that were really, the cameras, can take a picture of anything, but the instruments that told us about the chemistry were not designed to investigate a plume of material that was as tenuous as that which is coming off the south pole of Enceladus. They were designed to measure the atmosphere of Titan, for example, which is much more hefty. So it was a beautiful demonstration of how important it is to, first of all, be in orbit and kind of take up residence in a planetary system, so you have the leisure of discovering something and then going back to investigate it again and again and making changes in your approach.
Right.
And that's what we did with Cassini. But I want to add just one more thing about Enceladus, which fascinates me. 94% of the stuff that's being erupted from the South Pole of Enceladus, the particles, not the vapor, but the particles, comes back down to the surface.
Right.
It snows back down to the surface. So if there are microbes in the ocean of Enceladus that are being shot out, it's snowing microbes at the South Pole of Enceladus. So I think another thing we want to do is we want to go sample those particles and see if there are microbes in it. That's what I get really excited about.
That's pretty cool.
It doesn't get any cooler than that.
That's a holy grail. That's pretty fun. Now, and what do you do when you do that? Is that putting instrumentation down on the surface?
Well, this is very interesting.
Yeah.
We've all been discussing this. We're discussing how you might actually do this. And it just occurred to me recently, you don't need to land on the surface.
Okay.
All you need to do is really get into orbit around Enceladus. And the speed with which you pick up these particles would be gentle enough that you would not destroy microbes that were in the ice particles. And that's what we want. We'd love to be able to take a look at them. Now, whether or not we have the instrumentation now to do it is a question. Maybe, Chris, do you know something about this? The capabilities of microscopic imagers to do this sort of thing?
Actually, as you point out, we don't have a heritage in planetary missions of searching for life. We haven't done that since Viking, 1976. But meanwhile, NASA and other organizations have been developing technologies for studying life on Earth. There's been satellites in Earth orbit that have looked at biology, and these life sciences technologies can be applied to the search for life and be made suitable for planetary missions.
Life sciences technology?
Yeah,
what do you mean by life sciences tech? That sounds oddly like a life coach.
No, not that. What I mean is
not a lifestyle.
Not a lifestyle. Like what is the life sciences? Go ahead.
Well, we can think of two different jobs that we might do in space. One is take life from Earth and study it in space. That's called life sciences. The other is search for life on other worlds, life detection. They're both centered on life, but in one case, you're taking life with you and studying it. The other case, you're going somewhere and seeing if there's life there. But for example, a fluorescent microscope would be handy in both cases. Well, there's not been the development of such a microscope for planetary, but there has been for life sciences. People have taken these kind of instrumentation into orbit to study organisms that they've carried with them, to investigate the response of these organisms to the space environment. We can take that technology and repurpose it to searching for life in the plume of Enceladus.
Oh God, that's so great. It's so exciting. I can barely stand it.
That is
really. It's like it's waiting for us to go back.
Super cool. Yeah. Okay. Let's go on to another question. We have a little bit of time left in our segment, so let's grab another question from Nicole, coming to us from Twitter. At Cape Girl is her name. And she's talking with respect to astrobiology. What role, if any, would the study of planetary atmospheres and remote sensing have on the search for extraterrestrial life? So is there anything that we can glean just from looking at a planet that we know does not have life on it and look at the planet's atmosphere? And I'll go one step further and say even the planet's landscape from the standpoint of astrobiology, and find out about life or extraterrestrial life on that planet.
Okay, so I think, Chris, this is one for you. Did you get that?
Yep, I got it. And this is a really good question. It's a really good question, and it has implications right now on searching for life on other worlds, on other stars, exoplanets. If we see oxygen in the atmosphere of an exoplanet, I would take that as pretty compelling evidence that there is life on that planet making that oxygen. We can apply that same logic. We can't apply that logic to Enceladus. It doesn't have an atmosphere, nor does Europa. But Titan does. It's a very different atmosphere than Earth's, would have very different life. But we can take the same logic. If there was life on Titan, how would it change the atmosphere? And the conclusion seems to be it would be depleting hydrogen.
Chris, we have to take a short break now. We'll come back to what you're saying because it's really exciting, and we'll take more of the cosmic queries from our audience when StarTalk returns.
So the last time we talked about Blue Apron, I told you that my wife wasn't the best cook in the world, and I should apologize to her, but I'm not going to. Instead, I'm just going to order more meals from Blue Apron. Blue Apron knows that when you cook with incredible ingredients, you make incredible meals. So they set the highest quality standards for their community of artisanal suppliers, family-run farms, fisheries, and ranchers. So whether it's Japanese ramen noodles or wild-caught salmon or heirloom tomatoes, Blue Apron is bringing you the best. And when I say bringing you the best, I mean they actually pre-portion everything for you and deliver it right to your door. All you have to do is follow the simple instructions, put it in the pan, and cook it up. You've got a delicious meal waiting for you. Like, I don't know, spicy hoisin chicken stir fry with baby bok choy and sesame ginger cucumber salad. That was the last thing that we had from Blue Apron. And I gotta tell you, it was delicious. So here is what you need to do. Start cooking like an actual chef. Start cooking and making your friends jealous by putting those pictures on Instagram like everybody else does. Go to blueapron.com/allstars and get your first 3 meals free with free shipping. That's right. blueapron.com/allstars. Your first 3 meals free with free shipping. What do I have to do? Come over and cook it for you? Blue Apron. A better way to cook.
Bringing space and science down to Earth. You're listening to StarTalk.
It's just a matter of time. I'm ready to begin. My time is running in.
Welcome back to StarTalk Radio, All Stars Edition. I'm your all-star host, Carolyn Porco, and joining me in the studio is Chuck Nice.
Yes.
Thank you for being here.
Such a pleasure.
And
you're a delight, Carolyn.
well, thank you. And our special guest is Chris McKay, planetary scientist and astrobiologist extraordinaire at NASA, and he was in the middle of giving us an argument about what you might look at on a planet or a moon that had an atmosphere,
and how that would determine life. And you were talking about if you were to look at an atmosphere and see oxygen, you would know, or you would be able to strongly indicate that, hey, something created that, something biological created that. So can you go on from there?
Well, the point was, this is a very powerful technique because it can be done remotely. And the questioner indicated that, and this is true. This is the only way we could detect life currently around planets around other stars.
There's some question. Now, I would just be maybe the devil's advocate here and say that you could never really know to 100% confidence that that kind of a biosignature would give you, would mean life, but it would be a strong indicator, I think.
That's right.
Yeah.
It would certainly be very exciting to be an Earth-like planet around a sun-like star and find high level of oxygen in the atmosphere of that planet.
Yeah, I know people in that community who think that the only way you'd really know if we had life would be the interception of a signal from an extraterrestrial intelligence. That's like the only thing that would really give you 100% confidence. But it would be a red letter day if we found an exoplanet with.
Oh, that's fantastic. That's good. Well, Nicole, thank you for such a very well thought out question. Let us move on and ask a question from Doug Dumphy, who wants to know, what's the next likely mission to Enceladus, and what do you hope it is capable to do beyond Cassini? Hashtag CQ Enceladus, which is our hashtag. I don't know why I read that.
Well, you're just being.
I'm just being thorough.
You're being thorough,
maybe
right?
A little too thorough.
I think we just said that, but we can say it again.
Yes, we did. We did kind of get into that, but go ahead.
I was just going to say, Cassini has done a bang-up job unexpectedly because, as one of us, Chris, said, I think we didn't really. We suspected Enceladus might have geysers, but we didn't expect that it would. They would be. They would look the way they do and be as vigorous a phenomenon as it has been. It's just been an explorer's dream come true. And so what we want to do next is go back with instrumentation that is far better than that which was carried by Cassini, look at the chemical constituents to a finer level of detail, and look at abundances of compounds, look at, as Chris mentioned, the handedness of compounds, because, you know, earthly life prefers a particular type of molecule to another. Mm-hmm. And if we see that same kind of signature in on another planet, that might also indicate a process like life that has singled that particular type of molecule out. So those are the kinds of things we would look for. And like I said, one of my favorites is actually to grab and look at and image microbes. So that's the kind of things that we're talking about going back to Enceladus.
Nice. But the key is we are going back. Is that the case?
Oh, no, nothing.
What? What do you mean?
No, well,
why would you say that?
Well, there's a bunch of us that are really pressing for it, and we have the opportunity. We now can submit to NASA what are called New Frontiers proposals. So this is proposals for like a big chunk of money, something like $850 million. But that doesn't mean we'll get selected. There are people who want to go to Venus, people who want to go return a sample from a comet. There's lots of competition.
So now let me ask you this. I mean, this is just part of our conversation. And Chris, like you to know, I'd like both of you. I think it's terrible that we have to kind of
make choices
like this. These Sophie's choices where, you know, it's like, well, should we go to Venus or should we go to Mars or should we go back to, and so it's like, we should be doing all of this, to be honest. I mean, let's be very square. We should be doing all of this. So how do you prioritize, which missions should take place and when? Is there a particular protocol that should be in place to determine maybe this mission is important, but it's more important if we go now? Maybe this mission is important, but it really won't be important until, 2030. So how do you go about making the case for, getting these limited funds, which shouldn't be limited as far as I'm concerned?
Well, they are limited. And Chris, I'll let you deal with this. You're the guy who works at NASA.
Sure. But I'll tell you my way of prioritizing these, because I have to prioritize my time also. What do I work on? All the planets are interesting. I prioritize it based on what's going to tell us the most about biology now. And I think the clear winner is Enceladus. So I would answer, are we going to Enceladus? Yes, because it's clearly the place where we can learn the most about possibility of life right now. Other worlds are interesting too, but Enceladus is ready for investigation. There's samples there, as Carolyn said. It's a habitable environment. it's the low-hanging fruit. It's what we ought to do first, in my opinion.
Yeah, it's not clear. It's not clear it's going to happen. But Chris and I, that's why we're cohorts in this together.
Nice.
We're trying to keep Enceladus up front and center in the minds of people because it is, like you said, we're ready. We're ready now. We know enough to go back and do the job right.
Nice. Fantastic. All right. Good stuff. Good stuff. Let's move on and take another question. This one a little bit more broad from Kabir Malhotra. I'm terrible. Carolyn, you will know the more you do this. People like to, and Chris, you will know because I'm sure you will return as a guest. People send me their names. And
you have no idea how to pronounce it.
And I butcher their names like you can't believe. And I think that they're doing it on purpose now. I really do. I think people are just sending me made up names
just to
see me squirm and struggle. And because, but anyway.
At least they're listening.
This is true.
Okay.
Exactly. So this is, I hope I'm saying, Kabir Malhotra. Okay. Assuming the universe is infinite. That's a big assumption right there. I mean, is the universe infinite? Because I really don't think it is. But anyway, I'm not answering these questions. You are. But how long will it take to produce an exact copy of Earth? I don't think he means exact copy of Earth, but an Earth-like planet. Just, basically our Earth. So an exact copy is ridiculous because, that's ridiculous to say an exact copy of Earth. That's just never going to happen. And by the way, the Earth is changing all the time. So what would that exact copy be?
Right.
Because the Earth that we live on today is not the Earth that was here 4 million years ago.
That's right.
So it's a completely different planet now. So, but how long would it take to produce an Earth planet?
Well, I'm going to turn this around because that's very difficult to answer. So I'm going to turn it around to something that's possible to answer.
I like the way you work.
The Kepler results of how many exoplanets there are and what characteristics they are. This is Kepler with follow-on Earth-based observations from telescopes like Keck. Have indicated something like 25%, I hope I get this right, 25% of the planetary candidates that they find in the habitable zone of their star are Earth-sized. Okay?
Oh, okay.
I think that's right. And then some fraction of those would be Earth-like, and you could call it, Earth's twin.
Right.
And I don't know, someone took a reasonable guess, maybe let's say 20%. It's common. Nothing on our planet is unusual. That's what we've been able to glean about the universe is, what we have here is probably lots of other places.
Right.
So 25% of the planetary candidates in their habitable zone are like Earth-sized. Let's say 20% of those are Earth-like, which means like the Earth, okay, the copy. And when you go through all the numbers, the last time I heard this, which was probably 6 months or a year ago, the number came out to something like 4 billion Earth-like planets in our galaxy.
Oh my, that's
right
just
now.
Here, right now.
Right, Chris? Do I got that right?
The gist of the argument is certainly correct. There are going to be in our own galaxy a lot of Earth-like planets. We just got to look. We know that there's lots of planets out there, and some of them are going to be like Earth. We don't need an infinite universe. Our own galaxy, in fact, our own stellar neighborhood probably has lots and lots and lots of Earth-like planets, arbitrarily closely similar to Earth.
Really, we might have a lot of community work ahead of us.
Yeah. Wow. So, I mean, that's pretty unnerving when you think about it, because now
unnerving.
Okay.
It's like,
it's just
it's incredibly exciting.
It is exciting. When I say unnerving, I mean in a good sense. In a good sense. It is really that exciting that it's unnerving. It's shocking is what it is. It's shocking. So now let me ask the both of you this. With that in mind, does it necessarily increase the likelihood of there being intelligent life on one of those planets, since we pretty much developed on this planet? Does it increase the likelihood, or does it not? I mean, are those two things related in any way scientifically, or I mean,
Well, look, we have a statistic of one.
Right.
We know on an Earth-like planet, one civilization has developed to the point where we call ourselves intelligent and we are capable of communicating across space. So, if it happened once, it's likely to happen again. How likely is it? I don't know. I guess that's a guess, but I'm an optimist. I think that probably it's happened many times. Chris, do you want to take a guess? What do you think? You're an optimist, I know.
I am as well, and I think it's useful to divide the question into two steps. One is the distribution of life, and then secondly, the distribution of intelligent life. Certainly, we think that life should be widespread. Whether some of those life forms develop intelligence is a more deeper question, but I tend to be an optimist too. So I think we're going to find the universe is full of life, and that many, but not all, of those life-bearing planets have developed intelligence.
Gotcha.
That doesn't mean that they're like on their way to get us right now. It's the distances are prohibitive.
Yeah.
When you say a star is 12,000 light years away, that we're talking that's the time it takes light.
Right.
The fastest thing we have to get here. It would take us far, far longer than that. So,
yeah. So the realistically, life could exist there, but our being able to get to that life is very unlikely.
well, eventually, I suppose we could put some robotic spacecraft on a course for some star, and maybe
that makes sense. Yeah.
Yeah.
Robot. I mean, that's so that brings me to another question from both of you. Okay, especially you, Chris, being an astrobiologist. Is it more important to have a first contact from one of us making contact with intelligent life, or from an emissary that we have created, i.e. a robot or android or, some representation of human life, whether it's a computer or what have you. And, of course, that probably will make more sense because we can send that thing out and just let it go. We don't have to feed it. We don't have to worry about it dying, and it's not going to bitch and complain like I'm lonely and I miss my family. And so, So, I mean, is that most likely how we're going to make our first contact?
We might have made a first contact already.
Ooh.
We have our signals sent out. What did Dan Wertheimer just say? He said 70 years ago.
Right.
Something like that. So we won't know. That's the thing about this whole thing. The distances are so huge. We won't know if we've made a contact with another civilization until we hear back from them.
Gotcha. Interesting.
Yes. Okay. So we have just limited time. So we're going to wrap this up for this segment. We'll take a short break. And when we come back, we're going to entertain more of our listeners' cosmic queries when StarTalk returns.
You wear underwear every day. Well, at least most of us do. It's time to try something better. MeUndies has created the world's most comfortable underwear with a blend of fabric that's 3 times softer than cotton. When you feel awesome on the inside, you look awesome from the outside. When you upgrade your undies game, everyone wins. Life feels better in MeUndies. MeUndies is made from modal, a fabric that's 3 times softer than cotton. MeUndies has tons of colors and patterns from classic to bold to adventurous. And the only brand that has matching pairs for men and women. All orders in the U.S. and Canada ship for free. And if you don't love your first pair, and believe me, you will, MeUndies will pay you back and you can keep it for free, no questions asked. For a limited time, MeUndies is offering you 20% off your first order at MeUndies.com/allstars. That's right. MEUNDIES.com/allstars. And if you don't love your first pair, it's free. So make sure you go to MeUndies.com/allstars and get 20% off your first order. Hey, maybe you love books, but you never have time to read them. Well, Audible.com has the perfect solution. Get audiobooks and listen to those books you've been meaning to read while you're on the go. Whether you're at the gym, during your commute, Audible.com has audiobooks from the leading audiobook publishers, broadcasters, entertainers, magazine, and newspaper publishers, as well as business information providers. Their app is free and it works on iPhones, iPad, Android, and Windows Phone. You can also download and listen on your Kindle Fire and over 500 MP3 players. And unlike streaming or rental services, with Audible, you own your books, so you can access your books anytime and anywhere right from your smartphone. Audible.com also has the great listen guarantee. If you decide you don't like the book for any reason, no worries. You can exchange any book you aren't happy with for another title anytime, no questions asked. And for listeners of StarTalk, Audible.com is offering a free 30-day trial membership. So go to audible.com/StarTalk today to start your free trial. Again, audible.com/StarTalk and get a 30-day free trial and support StarTalk while you're doing it.
Hello again, and welcome back to StarTalk Radio, All Stars Edition. I am your all-star host, Carolyn Porco, and joining me in the studio is my fabulous, wonderful, dynamic co-host, Chuck Nice.
Hey.
Thank you.
Well, thank you. For a moment, I started to look around to see who else was here.
And we have as our special guest, we have Chris McKay, who's an astrobiologist from NASA Ames Research Center in the Bay Area. We've been talking about the search for life in the solar system. There isn't a topic that's more exciting than that. And we're going to now discuss what kind of life we might find on a place like Enceladus, and how might it be different than the life we have here on Earth? This is a really tantalizing question, because I think most people would agree it would really be far more interesting to find life that was entirely different from the life we have here, biochemically, metabolically, all those things, because then we'd have a point of comparison that we could make, and that would give us insights into how life developed one way on one planet and one way on the other. So, Chris, why don't you weigh in on this for us, because I'm sure this is something that you've thought quite a lot of.
Sure. Normally when we talk about different life, we're thinking something exotic, like maybe silicon-based life or something. And that's not what we're going to find on Enceladus. Enceladus is a world with water and carbon. How that carbon and water arranges to form biochemistry could be very different on Enceladus. So, for example, DNA, which we use to store information, may not be the same molecule used on Enceladus. The proteins on Enceladus may be made out of amino acids, just like the proteins on Earth, but they may be made out of different amino acids. Or the chirality, the handedness of those amino acids might be opposite. So there's many ways that life on Enceladus could be very, very different than life on Earth, and it would be very interesting to do that comparison.
Now, for us to do that, I'm guessing that that's going to be pretty hard to do with the kind of stuff we're talking about that might be done on the very next mission to Enceladus. I'm going to guess that in order to do that, we really got to bring samples back to Earth. Do you agree with that?
I think we could go a long way with instruments that we send there.
Okay, so you're talking about chirality or handedness, but what about the way its proteins are structured, or the way the amino acids go together? That's really higher order stuff. That's hard to do without bringing a sample back. Don't you agree?
Sure. We won't answer all of our questions. But we'll answer.
Sounds like you've got some life form there crawling around.
Yeah. We won't answer. He wants to go.
Oh, okay.
We won't answer all of our questions, and more complex questions will require more complex instrumentation. But we will be able to answer some questions, and if there is life there, we have a good chance of determining that it's there and determining that it's alien from Earth life. Now, eventually, yes, we do want to bring a sample back to Earth. The level of sophistication we'd like to apply to investigating a different type of life is the state of the art, and to do that, you need to bring the sample back. But we can make a lot of progress if we send the right instruments.
Okay, so let me, this is our last segment, and I just wanted to open it up even more, if I could, Chuck.
Go ahead,
that all right?
please.
In the Saturn system, there's another tantalizing place, which is Titan. Right. Titan is considered kind of, believe it or not, we used to think of Venus as the sister planet to Earth, but Titan is even more like Earth in many respects than Venus is. It has landforms that are like we have here on Earth because it's got a substance in its atmosphere, methane, which acts like water does here on Earth, and it rains out of the sky. It can form clouds. It can carve channels and gullies and so on. It can pond on the surface. And in fact, it's doing that. In the polar regions of Titan, we have found seas of liquid methane.
Wow.
Laced with ethane. So, I mean, think of, Lake Michigan brimming with paint thinner or something like that.
That's not too far off in the future. If we keep going the way we're going right now.
Now I'm not a fan of thinking that we have life in the seas of Titan because, or at least, I should say that we have a chance of really recognizing it because it would be so different than we have here on Earth because we know about earthly life. But I know Chris is a big fan of this idea, so I wanted to give Chris the opportunity to elaborate on the possibility that we could have life in Titan seas, given that the temperature there is so cold and the kinetics are going to be so slow and so on. And then how we might go about even recognizing life in the Titan seas.
Well, this is a really good question. And it roots to what do we think life needs? It's clear that life needs a liquid. On Earth, that liquid is water. The only other liquid that's widespread in the solar system is the liquid methane and ethane on Titan. So could life use that liquid? Now, it's very different than water. If there's life on Titan, it might be consuming hydrogen. And we might be able to detect that atmospheric effect more readily than we could actually detect the life form because we don't even know what kind of molecules to search for.
Yeah, right. It doesn't use amino acids. So it's going to be significantly different. It's just a challenge in the space program. It's a challenge to, like I said, this is where the rubber meets the road. You have to design an experiment. You have to know what you're going to measure. And when you're looking at an environment that's alien to the Earth and life that may not even be constructed like the Earth, that is no common biochemicals, it becomes very challenging.
Yes, that was fascinating. That was great stuff. Great stuff. I'm still fascinated by just the fact of life living in a methane ocean. That alone is kind of mind-boggling.
Yeah, well, they say, was it Rudyard Kipling that said travel is mind-expanding? Well, planetary exploration is mind-blowing.
There you go. All right, let's take a question. Drew Davenport. And Drew Davenport is writing from Wilmette, Illinois, here on planet Earth. He actually put it that way.
Oh, that's good. We want to,
have you ever found anything that you couldn't identify or thought was really strange during a spectral analysis? This is for both of you, actually, because I'm sure that spectral analysis is part of both your missions.
Oh, major.
Yeah. So now, is there anything that comes back where you're just like, that's odd?
Well,
strange.
I'm not a spectral analyzer myself, but I remember in the early days of the Cassini mission when we were looking at the results of one of the spectrometers on board Cassini that had scooped up material in the plume. And there were some signatures that they couldn't make sense of. And I think at first, in fact, they made a tentative identification, which did not turn out to be correct, and it turned out to be salt. They had not thought that there would be salt. And when they went back and said, okay, maybe this is salt, and they went back and did the match, it was a great match. So that's my little anecdote. Chris, you must have one.
I remember when we were first going to Titan, we thought it had a global ocean. When we got there, it didn't. And I think we have to keep that in mind. Our guesses of what's out there are often wrong.
Right.
The only way to know is to go look.
This brings up something that I love to just remind people of. In being explorers like we are, You know, we're kind of if not our bodies, our minds and our emotions are on these robotic spacecraft that we send across the solar system. And, you know, they find things that are, you know, we say, oh, my God, that's so surprising. We felt that way about the Enceladus plume. We felt that way about the distribution of the hydrocarbons on Titan. We all felt that way about Pluto when New Horizons got to Pluto. Oh, my goodness, look at this. These regions where you have ice convection and these polygonal features. It's not so much that it's a failure of knowledge. It's a failure of imagination. We understand physics pretty well and chemistry. We understand what happens at various regimes, physical regimes, but it's just that we don't spend an infinite amount of time imagining all the various permutations we might find there.
Right.
And when we get there, we end up being surprised. Like, take the Enceladus geysers. We knew post-Voyager, this was after the Voyager mission, a couple of years later, a paper was written about the possibility that we could have water geysers on Enceladus.
Right.
All right. It was suggested that these geysers, they might not have been called geysers, but they would be producing particles that would go into orbit around Saturn to produce the E-ring in which Enceladus is centrally embedded. So that was the connection. So we had geysers on the brain when we went back to Enceladus with Cassini, and the imaging team, planned observations to look for them. And the first image that we have of a plume coming off Enceladus has the word plume in the title of the observation. It was deliberately planned to search for plumes.
Right.
So we knew what we possibly might find, but nobody took the time to imagine, well, okay, so we have geysers coming off Enceladus. The gravity on Enceladus is only 1/100th of the gravity here on the Earth. So these things are going to be enormous. No one thought that.
Right.
So we get there and we see this incredible spectacle. And it just reminded me of this, that, you know, we always fail to imagine what we might find. So, it's what it makes it so thrilling, you know, just seeing something for the first time. It's just, it's mind blowing.
That's pretty cool.
Of course it's cool.
Excellent stuff. All right, let's actually Theron, and coming to us on Twitter at Astro Theron, not to be confused with Charlize
Theron. maybe that's a fan of Charlize.
Says, ask this. I really don't understand this question at all, so you guys are going to have to help me. Given similar environmental challenges, i.e. liquids behave the same, is it possible for exobiology to produce a species similar to us?
So we have only about a minute.
Oh, yeah,
so you're saying given similar biology? Is that the similar chemistry?
Yeah, similar environmental, yes.
Should we expect something similar to us?
Yes. In other words, is that are we more likely to find something similar to us given the similar situations or environmental situations, or should we be using our imagination to look for what you just said?
Okay, well, So using your imagination for every permutation would take quite a bit of time. I think this is a question that really devolves to this. What in the evolution of life, what role was played by basic physics and chemical laws, and what was played by serendipity? What was, a meteor hit the Earth and destroyed the first experiment, just wiped out all life that was just getting started,
right.
And then giving something else the opportunity to evolve. Like, the dinosaurs being wiped out open up the way for us. So we're going to have to wind down now. And thanks to our co-host, Chuck Nice. It's been a pleasure, Chuck.
The pleasure's all mine, Carolyn.
And thanks to Chris McKay, who's joining us from Ames Research Center for his insights into the origin of life.
Pleasure.
You've been listening to StarTalk Radio All-Stars Edition. I've been your All-Star host, Carolyn Porco. Until next time.